Greetings, the Astro 30 here again with another experimentational video. What we're going to be looking at today is, well, a circuit that's not new, or a concept that's not new. This has been around for many years. The OpAmp based power amplifier. Now, in this current configuration here, it's only going to be a low-powered power amp, but theoretically you can actually split where these two transistor and biasing network here connect to the plus 15 and minus 15. You could split those power rails and have a separate 15 volt, minus 15 volt going into the op amp and a much higher current power supply going into the power transistors. However, how high a voltage you put through these power transistors is dependent on the power transistors' ratings. Now, in this arrangement I'm depicting BD139 for the MPN and BD140 for the PNP. You could use much higher power transistors such as the MJ-L range or a 2SC 3263 and a 2SA1294 complementary pair respectively. In fact, in this experiment I'll be using both the C3263 and the A1294 because those are the only decent power transistors I have. I could always go out and buy some BD139s and 140s. In fact, I probably should, but for all intents and purposes what we're looking at here is basically a headphone amplifier. Now, we're using an NE5532, the original circuit used an LF356, but any generic op amp will do. In fact, the NE5532 would be a better choice because it has a higher slew rate. Now, I've got our input coming through a capacitor, 1 microfarad, going through a stopper resistor 1K. This is to try and avoid as much RF interference being present at the input as possible, in conjunction with this 330 picofarad going to ground. We've got a 100k biasing resistor for pin 3. Our feedback network is formed at the output of the transistor stages between these two 22 ohm resistors via this 100k resistor and this 22k. These current resistors give us a gain of roughly 5.5. The output of the op amp goes through what's known as a self-biasing stage comprised of these two 1K resistors and this string of 4 1N4148 signal diodes. The NPN transistor's base comes off of the anode end of the string, and the base of the PNP transistor comes off of the cathode end of the string, and the two emitters via these two 22 ohm resistors form a push-pull emitter follower. That's basically all to say about the circuit, apart from these 100 nanofarad capacitors on the supply lines here. They're what's known as bypassing capacitors, and these need to be as close to that IC as possible. Hence why they're drawn, well, close to the IC. So that's the concept. Now, does it work? Well, that's the next thing we're about to find out, if it does work. Now, just one more thing about these output transistors here. Just take note that there is no short circuit protection, there's no VI or voltage current limiting for the output devices. So if the output was suddenly shorted to ground, even at this low power of plus minus 15 volts, these output transistors will be instantly destroyed. Keep that in mind. And also, if you were to use this in a higher power sort of arrangement, where the output transistors had their own separate higher power supply, like a plus minus 35 volt, I would strongly recommend A, having inline fuses with each device, and B, I wouldn't use this topology with single transistors. I would either go a complementary compound pair, like C-Clay-E, or a Darlington configuration, so you have a separate driver and an output stage, or use complementary pair compound Darlington transistors. That is, the transistor is already a Darlington inside internally. So I'm going to be using different output transistors than what's already stated here, as I previously said. We'll see how it works. If it works, it should do. I mean, this is a common circuit. But we'll see if it works with the configuration I want to use it in and how much power output it can produce. Okay, short time later I've got the circuit built. As messy as it is, it's still functional. Now, I haven't actually powered it up yet. I'm just going to make sure that nothing is shorting against each other because it's a good tendency for it to do so. I haven't powered it up yet. I was waiting for it to be on video before I started. So I want to make sure nothing's shorting. I've got the transistors mounted on a heatsink with isolators and wires coming off the transistor leads into the breadboard, because obviously the transistor leads will not fit in the breadboard directly. I've got the power supply sitting there at 15.2 plus minus, and I've got the multimeter connected across the output on the millivolt scale. I haven't powered it up yet, but the only thing that can happen is the output transistors go off with a bang, and hopefully spectacularly. They're rated at 250 volt, 15 amps, something like that. So for the low power that we're working with, it should be fine. Now at the moment the output is unloaded bar the multimeter. So if we suddenly see a jump in current, we know there's a problem. So I'm going to turn it on, and we're drawing currently 60 mA, and the DC offset is less than a millivolt. So I'm just going to check the output stage for unusual heating. There doesn't appear to be anything getting hot there. So now we need to put it into a dummy load and a oscilloscope. Turn that off for now. And well, see what the output sine wave is. Okay, everything's set up. I've got the oscilloscope sitting there in the background at 5 volts per division, 1 millisecond per division. Got the DDS set to 1 kilohertz, 100 millivolt peak to peak for a test at the moment. I'm keeping the voltage down, or the output voltage of the DDS down low, and then I'll increase the output voltage and find out what its input sensitivity is on that circuit for full output without clipping. So I'm going to turn the load on, look at the current draw again, and also look at the oscilloscope output to see if I've got, well, a sine wave. I can see something on the oscilloscope, and I've got 50 milliamp draw. Not much happening on the oscilloscope, but there is an output there. So if I increase the volts per division to 0.2 of a volt, it's noisy, but it's there. We've got a V peak roughly, V peak to peak roughly of 600 millivolt. So it's not very great, but that's only with a 100 millivolt input. So I'll set that back to 5 volt per division. Now I'll start winding up my amplitude and watch the oscilloscope. And the oscilloscope's saying 3.6 volt peak to peak. Just going to check the output stage heat. There isn't any at the moment. So keep on going. 700 millivolt, 800 millivolt, 900 millivolt, not clipping yet. 1 volt peak to peak. 1.1, 1.2, 3, 4, 5, 6, 7. We're starting to clip now, I think. So I'll just decrease my volts. Yep, I can see it starting to clip. So I back that off, the clipping goes away. Yeah, we're clipping there. I'm going to say roughly 1.4 volt peak to peak input for full output, which is 6.49 volt. Okay, very good. Those transistors aren't even getting warm, but they are on a pretty decent heatsink. Okay, so we're at 6.49 peak to peak. Divide that by 2. Gives us 3.2 roughly. So multiplied by itself, square it. gives us that. I can see right away it's not going to be much output power, divided by the load, 1.3 watts. Now that's understandable. The actual circuit here is designed to power headphones. Now if you wanted more power out of it, you would have higher voltage power supply lines coming in using the current output transistors I'm using, or MJL series, whatever, or even a TIP31 and TIP32C respectively. You could probably get 20 watts out of the transistors, but in its current configuration, because it's now sharing the plus minus 15 volt rails, well, you're only going to be able to get it to output to those rails. 1 watt driving into a speaker is not very loud, but it's considerably loud. If you increase the gain of the amplifier, that means its input sensitivity, the amount of voltage you can put into it, is going to be lowered. So the higher the gain of the amplifier is, the lower the input voltage needs to be to give it full output. So increasing the gain would not gain us any extra power, because we're still limited to the plus minus 15 volt rail. However, we're not swinging anywhere close to that plus minus 15 volt rail. We're at least a good 7-8 volt peak to peak difference, or I should say we're at least a good 7 to 8 volt to the peaks difference from the plus minus 15 volt rail. And that is attributed to the drop in the transistors, as well as how hard they're being biased on, and those two 22 ohm resistors. If they were lowered slightly, you'd probably find you get a little bit more output swing. If this was going to be a higher powered amplifier, I'd probably change these 22R resistors to 0.22R respectively, and they'll give it a little bit more of an output swing. But currently, even at a gain of 5.5, we're not going to get any much more power out of it than 1.3 watts, which is average. These transistors are not getting hot, neither is the dummy load. I mean, 1.3 watts is not a lot. So the concept works, and currently with it running at full power, we're drawing around about close to 300 mA. Yeah, pretty close to 300 mA. It's 250 mA, something like that. So as a headphone amplifier, it'll work fine. Now the question is, what does it sound like going into a speaker? Well, because it's only 1 watt, it's not going to be very powerful, but, well, we can certainly find out. But of course, before we do that, it might be a good idea if we look at what the frequency response of the amplifier is and see how flat it is. So I've got it on sweep mode at the moment. Doesn't seem to be too much drop in voltage output. We're getting about 6 volt in the 20 kilohertz range. So it starts off around 6.2 and then slowly drops off to around about 6 the higher the frequency goes. So it's not a bad frequency response. Not exactly flat though, but yeah, now let's hook it up to a speaker and hook it up to an audio source and actually see what the sound sounds like. But the thing that is going to really affect the frequency response is this capacitor here. You could change that probably to a 10 microfarad or even a 47 microfarad, somewhere around that range, to get maybe a bit more bass response out of it. But we'll see what it sounds like in its current configuration and go from there. Alright, I haven't hooked it up to an audio source yet, but I have hooked it up to a speaker, so I'm going to turn it on and see if there's any unusual noises coming out the speaker. There's circuit noise, circuit buzz. Yeah, I can hear that there's not much bass response there, but we'll hook it up to an audio source and see what we can get out of it. Alright, got the CD player hooked up. Not much noise coming out the speaker now that I've got a pot there and everything is terminated. Slight little buzz there, but nothing unusual. Play and see what happens. Not a great deal. There we go. Better. Now I've got an issue here. My input was shorting. What I might do is I might change that 1 microfarad capacitor there to a 10 microfarad and see if that gives us a better bass response. Okay, got the 10 microfarad in now. Let's see what happens. Not sure if that made any difference or not. One of my leads just popped off. Excuse me. Okay, it sounds alright, for albeit 1 watt. It's not really high powered, and these transistors are overkill for the actual circuit that it's really designed to do. It's designed to power headphones. You wouldn't use high power transistors like that, as I have done, but I did it because, well, that's what I had and that's what was convenient. So let's get on to my conclusion. So in conclusion, the circuit in its current configuration works, and it works very well. I'm using a complementary pair Sancan transistors 2SC3263 for the MPN and 2SA1294 respectively for the PMP. Now, I'm not going to modify this circuit to run on higher power and add in, you know, like shunt regulators for the 15 plus minus rails there and stick 30 volt across these transistors, because really in this configuration, as I previously stated, it's okay, but you'd really want a better output stage to drive speakers to a higher power. This will work, but the possibility of thermal runaway on the output devices, because you've got no control over the biasing, is quite strong. But for use as a headphone amplifier with a BD139 as an NPN and a BD140 as a PNP, mounted onto a heatsink, mind you, will work just fine. And because this is an NE5532, it's a dual OpAmp, you can use the other channel of the OpAmp and a secondary output stage there to drive the right hand channel. But in its current drawing here, it works fine, and it may become a circuit that I'll use somewhere else later along the line, because I know it works. But for now, we're going to leave this here. This is not in any way, shape or form the power of op-amps. This is just one application of an op-amp. There are various different applications for an op-amp. There's like comparators, there's voltage controlled oscillators, there's power supplies, you know, voltage adjustment on power supplies, current adjustment on power supplies using op-amps, switches, all sorts of things you can use an op-amp for. This is just one application. Originally op-amps weren't really designed for audio, they were designed for arithmetic operations, but for now we're going to leave that here. You could probably drop these string of 4 diodes down to 2, which is the more customary way of doing it. But this one was done with 4 to try and keep the crossover distortion as low as possible without having to add in an adjustment pot somewhere in the string here to adjust the bias of the output stage, and to try and keep it as linear as possible. It'd be a lot better, as I said, if you had, say, a complementary pair, a complementary compound pair such as a C-Clay or a Darlington output stage, because they'll help keep the output as linear as possible with mismatched devices. But if you're going to use it in this configuration, you want to get as close to match devices as possible, which in the real world is, yeah, anyway. So that's it. I will draw up this schematic properly and put a link in the description to it if you want to muck around with this, modify it, you know, make it better, whatever. Just one other thing to note here with this design, I've used 1/2 watt metal film resistors here for the 222 ohm resistors. They're very underrated for the job. I would consider quite strongly, because they were getting quite hot when it was driving the speaker, and this one started to discolor, meaning it's starting to burn. At least 1 to 2 watt devices. 5 watt would be excellent there. But this was only just for a test. I mean, you know, if it caught on fire and burnt out, well, who cares, right? It's only like a 5-cent component. But yeah, those resistors are underrated, so don't use 1/2 watt ones, and definitely do not use 1/4 watt ones. They will fry up instantly, even driving a pair of headphones. I was driving a very capacitive reactive load such as a loudspeaker, which is a little bit different to a pair of headphones, but yeah, over the long term these resistors will cook even with headphones. Another thing to consider here on the output would be a Zobel network, which would just simply be having a resistor of 10 ohm and a capacitor to ground of 100 nanofarad. That will help prevent the high gain, well, it's not really high gain, but the amplifier stage here from going into ultrasonic oscillation, which will start heating up output device transistors very quickly. You could also add a small coil and another 10 ohm resistor in parallel with each other on the output leads, which will help if you're driving capacitive loads, such as a loudspeaker on long speaker leads. But nowadays it's been found really through testing that having the output coil and resistor network there isn't really needed. But it depends. The reason why a lot of amplifiers have a coil like 0.7 microhenry or something like that, and a 10 ohm resistor or a 4 ohm 7 resistor in parallel with it, is for driving capacitive loads. But that's the whole entire circuit tested. As I say, those 22 ohm resistors are underrated for the job. So be sure to use at least 1 watt devices. But anyway, it's working. It works reasonably well. It sounds alright, yes. As an amplifier to drive a speaker, no, not so much. But it'd probably make a very good Class AB headphone amplifier. The only thing is it has a fairly high quiescent current draw of around 60 mA. But that could be dropped by sacrificing a little bit of crossover distortion by adding a trim pot of 10k or so across the between this anode of this diode and that resistor, 1k resistor there, just so you can adjust the forward drop to the output stage. As it stands, it's fine. It's okay as it is.
Thanks for watching, and don't forget to subscribe to the Astro 30 for more great videos. Remember to hit the little bell icon next to the subscribe button so you never miss a new upload. You can also follow on Twitter and like on Facebook. The links are in the description.